let's start on our lecture. Last time we started discussing this important topic, estimation. Estimation. Well, it's about parameter estimation. Let's start with some revision. Okay, we assume that each member in the population under study possesses a certain individual value of a numerical characteristic. And by choosing at random one member from this population, we create a random variable x that is called population variable. All right, what does this estimation refers to? We assume a certain law, the probability distribution for this x, assumed law, but in this assumed law, some parameter is unknown, and the most common situation is that mu is unknown. Mu stands for the mean or expected value. And when estimation is described, this estimation procedures are described in textbooks, the accepted notation for the unknown parameter is theta. Theta. Okay. Well, and how do we go about estimating the unknown value of the parameter? We take a random sample of some size, and n, a lowercase, stands for the size of the sample. On the sample, we observe some specific values of this random variable, of this numerical characteristic, and a sequence of n numbers. These are the sample data. Okay? And the question now is this. Okay, we take a sample, we observe n specific numbers. How do we use them to estimate the unknown parameter, theta, or more specifically, mu? Okay, what's the best way to estimate the unknown parameter? Okay, now I must say that there is not just one universal optimal approach to this. Okay, there is no just one single best answer to this question. There are some criteria that are used. One of the criteria that can be used is maximum likelihood principle. Maximum likelihood. Okay. Now, what is this about? Given the sample data, what value of theta makes these values the most likely? This is the question that is asked. Okay? Let's illustrate this by an example. Let's look at the binomial distribution. Suppose x1, x2, xn are independent binomial variables with the same with the same value of p, which is the probability of success. Okay, and now p, we assume that the variables are all binomial and independent and have the same p, but the value of p is unknown. All right. Suppose we take a sample, and these are the observed values. Now, well, it's not really accurate to say this. Now, each of these is a Bernoulli variable, and put together they form this binomial distribution. So what does this mean in terms of the observed values? Because each of them is the result of a Bernoulli trial, the possible values, there are only two possible values here, 0 and 1. So each of these numbers is either 0 or 1. Okay? And k, the number of successes. Well, can be presented in this form. K, the number of successes, is the sum of all these x's, x1 plus x2 plus xn. Okay? Do you get this? It's if each of them is 1 if it's a success and 0 if it's a failure, then summing up all these numbers, we get the number of successes. And the question that we ask here is this. What is p? Okay? So we assume the law, it's the Bernoulli law, but p remains unknown. All right, let's do this. Let's write down the probability that these values occur given p. What's the probability of k successes in the binomial distribution? It's n factorial, k factorial, n minus k factorial. Okay, binomial distribution. And well, the right hand side depends on p. Because we are doing the maximum likelihood approach, we look at the maximum of this probability with respect to p. We ask the question, what value of p here maximizes this probability? Well, it's convenient to first take the natural logarithm of each side. Okay, it's logarithm natural n factorial, k factorial, n minus k factorial times plus k plus. Okay, so I just take the natural logarithm of each side. It's a technical thing. It's just more convenient this way. Because logarithm is an increasing function, the maximum of this function occurs at the same point as the maximum of this function. All right, and taking the derivative with respect to this little p, we get this. It's well, this first term doesn't depend on p, so in terms of p it's a constant, and it doesn't make any contribution to the derivative, and this is k over p plus n minus k minus 1 minus p. Okay, and collecting these terms, we can write it this way: k minus p times n, p, and the denominator is p times 1 minus p, and we equate it to 0 because we look for a maximum value. Okay, well, for this to be 0, p must be k over n. Well, I hope you understand what we just have done. We have applied this maximum likelihood principle. If we take a sample and the variable is of the Bernoulli type with the unknown value, with an unknown value of p, the value of p that maximizes this collective outcome equals k over n. And by the way, this is called sample proportion. Sample proportion. Okay. Well, let's. Oh, this is a problem. We don't have anything to use as a rubber. Okay, I have to interrupt. Пожалуйста, поищите, чем стирать. It's my fault. I didn't notice that. Так, пожалуйста, побыстрее, у нас съемка. Так, чья-то контрольная, думаю, никому уже не нужна. Okay. Sample proportion is a particular case of the sample mean value. Ну, проявите инициативу, ну, поищите где-нибудь. В субботу должны быть пустые аудитории. Найдите. Как ребенок вообще. Что мне делать? Рукавом, что ли, стирать? All right. Again, I'm sorry for these interruptions. So, sample proportion is a particular case of sample mean. We add up. So, these are the sample data. Data x1, x2, xn. And the sample mean is this. Okay? Well, and this is the maximum likelihood estimator if the underlying variable, population variable, is binomial or Poisson or normal. Okay? So this is for binomial Poisson or normal. Well, we don't say that this is the maximum likelihood estimator for the mean for any distribution law. Okay, it can't be. This kind of statement is not true, but for these three most important distributions, this is just correct. Thank you very much. All right, and now as I mentioned earlier, there is not just one universal criteria for the best estimator. The maximum likelihood principle is just one approach, and some other are these. Well, let's say that let's put it this way: properties of a good estimator. Okay. Well, it's generally considered to be a good thing. It's if the estimator is unbiased. Biased. Now, what does that mean? X, the population variable, has some value of the mean, of the of expected value, mu. An estimator is unbiased if its expected value is the same as the expected value of the underlying variable. Well, and this is true for x bar, for the sample mean. The expected value of x bar is the same as the expected value of the underlying variable. Okay. Well, then we hope that the estimator will be consistent. Consistency. Now, what does that mean? Well, in application to x bar, it means that if n increases, if n goes to positive infinity, x bar approaches mu in probability. In probability. The meaning of this was discussed at our previous lecture. Okay, I gave you a formal definition of this, and the theorem that exactly states this property is called the law of large numbers. Okay, please look it up in your notes from the previous lecture. All right, and also there is a property called efficiency. Efficiency. It means that the estimator has the minimum variance among the among the unbiased estimators. So minimum variance. Okay, and x bar satisfies this requirement as well. So x bar, the sample mean, is an estimator of mu, the mean of the underlying population variable that satisfies the maximum likelihood principle, the requirement of unbiasedness, consistency, and efficiency, which makes it the best estimator in many respects. Okay, does it mean that x bar, the sample mean, is an ideal estimator of mu always in any situation? Well, actually, no. The answer is no. Let's look at it this way. Well, the property that I'm going to discuss here is not typically cited as one of the requirements for a good estimator, but in practical terms it's important. What I mean is stability with respect to errors. Okay? Now assume that when you observe and record these values, you make an error. Well, we are all humans, we all make errors. And it's always possible that the person who just records the data makes an error. What's the effect of this on the value of the estimator? This is what I mean by stability. Okay. Well, is X bar stable? Now, let's imagine this very simple situation. Suppose we conduct a field research, a field survey aimed at estimating the mean body weight in a certain population. Okay, we take a sample of, say, 50 members, and we record carefully the body weights, but by a slip of hand, one of the weights is not given as 80, which is the right value, but it's recorded as 800. Is it possible? Absolutely. Just one more zero and you get 800. Now think of this. What's the effect of this error on X bar? Well, actually the answer depends on the size of the sample, of course, but if the sample is something like 30 or 50, which is already considered a large enough sample, the effect of this error will be catastrophic. X bar will have no relation to the true mu, to the true value of mu as a result. Okay? Do you understand what I'm talking about? So what is the effect of possible errors on the value of the estimator? And X bar, unfortunately, is rather sensitive to errors. Now, if we are specifically concerned about stability, then, for example, the median, sample median, may be a better estimator, because if one of the values is totally wrong and 10 times larger than it should be, or 100 times larger than it should be, X bar can be totally ruined, but the median will probably not change at all, or it will only change slightly, okay? It will shift from one data point to the next one, well, from the definition of it. So the median can be a more stable estimator. And if we are after stability, it may make sense to consider the sample median as an estimator. Okay, let's move on. Well, this previous discussion was about what is called point estimate, and point estimate is just one number. Okay, we assume a certain distribution law for the population variable, a distribution law such as normal or binomial, and there is a parameter that we don't know. Mean is the most common parameter. And a point estimate is just one number. We take a sample and say, according to our rules, according to our principles, this value is the best estimator of the unknown value of mu. Well, but if you think of it, this is not a very satisfactory kind of estimate. Okay? Well, suppose you're interested in estimating the mean individual income in a certain population, in a certain city. Okay? And you conduct a survey and estimate that the mean value of the monthly income in this area is 45,000 rubles. Okay, of course, this is some finding, this is some information, but if you ask yourself, how different can this estimate be from the true meaning? Okay, if you only have one number, you have no answer to this other question. Okay, this may leave you unsatisfied. Okay, you have a number, but you have no way of judging how different it can be from the true meaning, okay, from the true value. All right, now there is a different approach that addresses exactly this issue. and it's called interval estimate. Okay. Now, again, we assume that we have a certain population variable, x. Okay? And mu is unknown. Mu is the object of estimation. Now, also, it's important to know sigma. And to start with, let's assume that it's known, okay? Later on, we'll discuss a more general formulation of this estimation problem. Estimator that we use. So we have just found out that x bar is the best estimator in many regards. So x bar is the estimator. Okay. Now, x bar as a random variable has these parameters. Mu x bar is the same as the mean of the underlying population variable, and sigma x bar is sigma over the square root of n. Well, which means that we take a sample of size n here. All right. Now, now we make a very important step. We say, let's assume that the sample is large enough. Later we'll address the case where when the sample can't be considered as large. Well, practically, as a practical rule, it's accepted a sample is considered as large if the number of points is larger than 30, is greater than 30. Well, I must say that this is not a very theoretical thing. It can hardly be proved in any logical way, but it's a commonly accepted rule. A sample is considered as large if the number of observations is greater than 30. Now, why is this important? Why it's important to introduce this condition, large sample? The point is this. Due to the central limit theorem, x bar is at least approximately normal when n is large. Okay. Well, strictly speaking, as n approaches infinity, x bar minus mu over sigma divided by the square root of n. Well, this quotient approaches the standard normal distribution as n approaches infinity. Okay, let's put it this way. It's 0 approximately equal to 0, 1. Okay. Again, I've already done this, but let me do this again. I want to draw your attention to this absolutely remarkable fact. We do not assume any specific law for x, for the population variable. Regardless of the law for x, x bar will be approximately normal if n is large. This is absolutely fantastic, if you ask me. It's one of the laws of nature. It's one of the very important laws of nature. All right. And we can make use of this. How do we make use of this? Let's continue here. Well, let's write this equation. Okay. Now the right hand side here was my attempt to write the Greek letter gamma. Okay. I hope this is better. All right. So what do I mean by this? Let's set a certain value of probability that we denote by gamma here. Now, in just a short while, I'll comment on this. I'll explain what it means. So far, let's just say that gamma is a probability close to 1. Well, the typical values are 0.95, 0.9, 0.99, like this. So gamma is a probability whose value is close to 1. And then we can write this equation. We look for a value of d such that the probability that x bar falls within this interval is equal to gamma. If we draw this diagram, mu plus d, mu minus d. So this is an interval who's centered at mu. Okay, and d is the half width of this interval. Now, what do we say about this interval? We say that x falls within this interval with the probability of gamma. Okay. Now it's time to make use of this remarkable equation. We can rewrite it this way. It's minus d sigma root n less than x minus mu sigma divided by root n less than, I'm sorry, d sigma square root n. Okay. Well, maybe it doesn't really matter whether we use strong inequalities or weak inequalities here, but I think to make it consistent with some other formulas that I'm going to write, let's make them weak. All right, and this is gamma. So actually it's the same equation. I just rearranged these terms. I subtract mu from each term and I divide by this sigma over root n. Why do I do this? Now the middle term now is this standard normal random variable. Okay, let's write it this way. Z equals d sigma root n. Okay, so we look for a value. Look for a value of z that satisfies this equation. Okay. Please compare this and this. This is a diagram for x bar. Okay, and it says that x bar falls within this interval mu minus d to mu plus d with the probability of gamma. And this is the same story again, told again, but now it's told in terms of z. Okay, z that corresponds to this value of x bar falls within two. The normal, this normal standard normal random variable falls within this interval where z is gamma over 2. So this is gamma over 2 and this is gamma over 2, like this. Okay, and now we make a very tricky step. so far it was pretty transparent and clear, and now we do this. Okay? Well, actually, these two inequalities, this double inequality, can be rewritten equivalently, rewritten in this way. So we can write it this way. Okay? But again, I just said that this is a tricky thing to do. What is tricky about it? We must interpret this correctly. It's very easy to misinterpret it. Now look at this. The first thing that comes to mind when we look at this equation is this. The probability that mu gets within this interval x bar minus d to x bar plus d is equal to gamma. And please note that this is a wrong thing to say. Why is it wrong? Mu is not a random variable. Mu is something that is there. We don't know the value of mu, but it doesn't make it random. Okay? And because it's not random, it's not correct to talk about the probability of mu getting in some interval. Okay? Now, how are we supposed to interpret it if we can't interpret it this way? Now, mu is a number, a fixed number. It's an unknown number, but it's fixed. What is random about this is the value of x bar. So each time we take a random sample, we get a new value of x bar. And subtracting and adding the value of d, we get a random interval. So the random interval shifts each time we take a new sample. Now imagine that we take very many samples of the same size. Okay? And each time we construct this interval. Now, with this probability, the interval constructed in this way will capture the true value of mu. So this is the right way to understand it, okay? And we say that this is this is called a confidence interval to confidence level gamma. Okay. So how do we actually find d here? Now the order of operations is this. We set a value of gamma, typically one of these. Then we solve this equation, maybe using the table, which gives us a value for z. And then, so let's write it this way. Gamma gives us z, and then d equals z times sigma over root n. Okay? This is how it works. All right, let's give it an example. Well, last time we discussed the problem of estimating the mean body weight of a polar bear. And in this imaginary survey, we were not only very successful, we were only able to get one bear sedated. The sedative that we used didn't work very well, so we took only one measurement. But because we had some prior estimate for sigma, we still were able to come up with some estimate of the body weight. Okay, well, that was our expedition number one. It wasn't a big success, but next summer we went to the Spitsbergen or Franz Josef Islands, equipped with a much more effective sedative. Okay, this time we have a very effective sedative. Example, polar bears. So with this effective sedative, let's write it this way. X is the body weight of a bear, and mu, we are after estimating mu, and let me remind you that sigma is supposed to be known, or maybe it's taken from some historic data, and it's estimated to be 17 kilograms. Okay. All right, and now this more effective sedative allows us to sedate 80 bears, which is a big lot, 80 bears. And X, the sample mean, happens to be 398 kilograms. And now let's construct a confidence interval. Let's accept the most common value for gamma. Gamma is 0.95. And now let's solving this equation. We get this value. Okay, let me continue here. We get this value for z. Okay, whenever gamma 0.95 is applied, we have to use this value for z. All right. So what is the confidence interval? 398 minus 1.96, 17 over the square root of 80 is equal to 394.3, 398 plus 1.96, 17 over 80 equals 401.7. So the confidence interval, 0.95 confidence interval is 394.3, 401.7, like this. Again, does it? Let's look at this a bit longer and try to work out a correct way to interpret this. What have we obtained in this way? Are we certain that the true value of mu, the mean weight of polar bears in this region, lies within this interval? The answer is no. Okay, we don't know that. We can't be certain. We deal with random variables, and there is no way we can arrive at a certain, absolutely certain answer. But in a certain sense, this is a reliable interval. And now, how is this reliable? Again, the true way to interpret it is this. If we conduct this kind of research again and again and again, many times, and construct the confidence interval in this way each time, then 95% of the time, the interval constructed in this way will capture the true value of mu. Okay? So this is what we mean when we say that this is the confidence level for the mu, the confidence interval for this unknown value of mu, constructed at the confidence level of 0.95. Okay, this is important. By the way, when I just started this course, I promised you that I'll arrive at some practical things for you to use. Now this is one of the practical things. Whenever mathematical statistics is used, well, quite often, I would say 70% of the time, it's about constructing confidence interval. All right, so now already you know something useful for your future careers. All right. That was about interval estimate. But there is a weakness in this formulation. Maybe you noticed it. We started by saying, okay, mu is unknown, but let's assume that sigma is somehow known. And here we assume a certain value for sigma. This is a weak point because it's not very logical. We assume that mu is unknown, but sigma is supposed to be known somehow. Well, I wouldn't say it's impossible. Again, let's look at this example for, concerning polar bears. Now, we don't know what is the current state of this population, what are the physical parameters. And we are very concerned about the mean weight being reduced by these climate factors, by the global warming. That was the motivation for our research. So we suspect that maybe mu, the mean weight, is going down. That was the big question. But sigma, maybe, I'm not saying it's absolutely true, but maybe sigma can be considered as a more stable quantity. Maybe sigma can be borrowed from some historic research, maybe conducted 20 years ago. Okay? So let's assume that 20 years ago an extensive research was conducted and it was established that sigma equals 17. If we don't have anything else to use, we can use this historical value in the hope that, well, the inaccuracy, the inevitable inaccuracy in this parameter will not influence our findings very much. Okay? All right, but we don't have to rely on some historical data, and in some cases there are no historical data whatever. So what can we do if we don't have any estimate of sigma? Well, it turns out that it's not a lost case for us. We still can do this estimation thing. All right, so this is going to be the case of unknown sigma. Okay, if sigma is not known, then we can estimate sigma on the same sample data. So the same sample data, x1, x2, up to xn, can be used not only to estimate mu, but to estimate sigma as well. So, sample, again, x1, x2, xn, sample. And now, all right, this is called sample variance. Sigma squared hat. Well, as I already mentioned, this symbol hat indicates estimation. So sigma squared hat means estimate of sigma squared. And this is the estimator. S capital is the notation for this variable, and it's called sample variance. Okay. Now, if you look at this closely, you may notice something interesting here, something that may give rise to questions. Now, what about this denominator? If you recall the formula for the variance as it was first introduced, and reasoning by analogy, you might suggest that the denominator here should be n, and for some reason it's n minus 1. Well, it's an essential thing here. For comparison, let's write this. Okay, please compare these two, this and this. Well, do you notice this difference? Here we have mu, which is assumed known here, and here we do not assume that we know mu, we use x bar instead. X bar is the sample mean. Well, I'd like you to try to imagine this. I'd like you to understand it on an intuitive level. Of course, this can be proved rigorously. And what is proved is this. E of s squared, that is the expected value of this estimator, is equal to sigma squared, which means that s squared sample variance is an unbiased estimator of the population variance. All right. Again, let me try to explain why we have a smaller denominator here. What is variance anyway? Variance is can be explained to be the expected value of the squared deviation from the mean. Okay, this is the deviation from the mean. I'm sorry. This is an error. Please forgive me. Please correct this. So this is the deviation from the mean of xi, and we square each such deviation, and then we average them out. So the variance, which is a measure of spread, is the average squared deviation from the mean. And here in the numerator, rather than the deviations from the mean, we have deviations from x bar. Well, I'd like you to imagine it and accept this idea that the mean deviation from x bar will be a smaller quantity. So if x bar, because x bar is computed on the same sample, the mean deviation from it will tend to be smaller on the average than the deviation from the true value of the mean. Okay? Well, let me try to explain this idea. This is sample 1, and this is its sample mean. And this is sample 2, and this is its sample mean. Look at this. Here we take deviations of the sample points from the true mean, and this is mu. And here we take the deviations of the sample points from the sample mean. Because the sample mean is computed from the same sample points, the mean deviation here will tend to be smaller than the mean deviation here. All right, I'm not sure I've been successful in explaining it to you. Well, if you are after proofs, rigorous proofs, look it up in my handouts that I'm going to post. It's not a very long proof. It can be followed. All right. So the main idea is this: if we don't have an estimate, a prior estimate of sigma, and information, we don't have any information on sigma, we can estimate it on the same data points. And this is the estimate for sigma squared, and estimate and this is an estimate for sigma. So S, which is the square root of this complex, is used as an estimate for sigma. Well, there is a subtle point here. S squared is an unbiased estimator for sigma squared, which is exactly expressed here. Well, it doesn't really mean, and it's not true, that S is an unbiased estimator for sigma. It's not, okay? But still, this unbiased thing is not very important. It's not a big shortcoming of this estimator, so sigma is universally used as an estimate of sigma. S is used as an estimate of sigma. Okay, now let me remind you that if a sample is large, then x bar minus mu over sigma over root n is standard normal. That is just a reminder. All right, now we say we don't know sigma. We estimate it on the same sample, and we use S for sigma here. So we are dealing with a small sample now. We can't use this formula, and we use this instead. Okay. Now this is no longer a standard normal random variable, and there is a name for it. It's called, well, it's called students T distribution with n minus 1 degrees of freedom. Students T distribution. Well, there is a legend that the author of this distribution, the mathematician who discovered it, the name was Gosset. He was an employee for the Guinness Brewing Company, the famous company that makes beer. He was a statistician who worked for that company. But this is something that he did independently, and he published his results in a scientific journal. But the legend has it that the company discouraged its employees from publishing their results. Okay, so this guy Gosset published his famous work under an assumed name, under a pen name. He signed it student. Okay, so this historic work was signed student, and this is why up to this day, this distribution is called students T distribution. Now, what kind of distribution is that? Well, first, n minus 1 here is the number of degrees of freedom, and the notation is df, and df should not be understood as a product of something called d times something called f. df is an integral symbol, number of degrees of freedom, number of degrees of freedom. Okay. Please pay attention that if we have a sample of n points, the number of degrees of freedom is n minus 1, not n. Well, again, it can be treated rigorously mathematically, but we are not able to go into this here. Let me try to give you some intuition. Why is the number of degrees of freedom one less than the number of points used? Now, notice that we have already used these data points once when we computed x bar. So we have n deviations from x bar, but they are not independent. This is the point. The n deviations from x bar are not independent because x bar is computed on the same points. Okay. For that reason, the number of independent pieces of information here is one less. It's not n, it's n minus 1. All right. Now, what kind of distribution is that? Let me write it this way. PDF. Okay. So again, df is just a number, such as 1, 2, 3, and so on. I'm not writing this coefficient. It's a constant coefficient, a normalizing coefficient here. I'm not writing it in detail. It's rather messy. It's expressed through the so-called gamma function, which is not an elementary kind of function. And I'd rather not write it here. Again, if you're interested, please look it up in some textbook. What's important is this. This is a constant. Okay? This constant, it's a separate constant for every number of degrees of freedom. And if you look at the structure of this, you will notice that this is a rational function. A rational function. Okay? Also, because this exponent is negative, this rational function approaches 0 when t approaches positive infinity or negative infinity. And also because t here appears as square, the function is symmetric. So, even by just looking at this function, we can expect that it will have this kind of shape. And it must be familiar. It's a bell-like shape. So maybe, well, as a wild guess, maybe it's the same function as the normal distribution. Well, the answer is no, it's not the same function. It's a rational function, and the normal distribution is an exponential function. And how do these two relate to each other? Now, the relation is this. Okay, so for any value of df, the number of degrees of freedom, it's a bell-shaped curve. And generally it resembles the normal distribution. Well, actually, when df becomes very large, as df goes to infinity, the t distribution, so let's write it this way. T approaches as n goes to positive infinity, like this, okay? So the standard normal distribution is the limiting case, is the limit of t distribution when the number of degrees of freedom goes to infinity, okay? Which in practical terms means this. If n is large enough, again, as a practical rule, large is 30 or more, okay? If n is large enough, there is not much point in using this exact t distribution. The normal approximation can be used instead. The difference in the answer will be small enough. But if the number of points is small, then of course they are different, and the exact distribution should be used. Okay, I think I missed something. Small sample and normal x. Okay, please, identify this in your notes and add this important condition. So, a small sample. When we talk about a small sample, we make this important assumption. Additionally, that it must be a normal distribution. Well, maybe I'll get you interested if I tell you about a story from real life. Well, my father was a military engineer back in the 50s. He was employed in developing the anti-missile defense, if you know what this means, anti-missile defense. And well, he told me a lot of stories about that work. That was quite a huge project. Now, one of the features of this project, one of the conditions under which it was all done. Well, one of the conditions was this: whenever they received a certain consignment or shipment of anti-missile missiles from the plant, from the producer, this shipment typically was very limited, because each particular item was extremely expensive. Can you imagine that a missile that is supposed to hit a missile up in the sky? Well, each such item was very expensive, and testing them, and my father was exactly employed in testing them. Testing them was a very responsible kind of activity. It was important that it was responsible, and the task was and the job was to extract as much information as possible from very limited number of tests. Again, because testing a missile means destroying it. Okay, you can't use a missile twice, and each missile cost a lot of money. Okay, so that was the permanent headache for all the people that were employed in those tests, to obtain as much information as possible from very limited number of tests. And he told me when I was just a schoolboy, that every officer, every engineer employed in those tests, use this on the daily basis. T-distribution, invented by somebody, by an employee of the Guinness company, was used on the daily basis in this project. Okay, that was a piece of history. I mean, sometimes it's extremely important. Okay. All right. Let's give it an example. It will not be about missiles. It will be a peaceful kind of example. Suppose you are assigned by your superior manager to conduct a field survey. And the field survey is aimed at finding out the mean time that residents of a certain area spend daily watching TV. So, mean daily TV watching time. Okay. So you go out in the field and try to get people involved in this survey. But what you are faced with is that the reports received from the respondents are very unreliable. When you ask people how much time they spend watching TV daily, their answers can't be relied on. Okay. Well, a respondent may say that it's only 30 minutes, when in fact it's 3 hours. Okay, but the respondent understands that it doesn't sound nice. 3 hours is a lot of time to spend watching TV, and many respondents give inaccurate answers. By the way, it's a big problem in practical estimation activity. Okay, inaccurate, false answers. All right, because you understand that, you insist on actually visiting homes and monitoring the process, okay, for some period of time. So, and this is something that people do not like very much. Only a few agreed to accept you as a guest in their homes and let you monitor the process. So, to sum up, you only convinced 10 people to take part in this survey. So N is a small number here. And you are lucky to have even this number of participants. All right, and what you find on this sample is that the average time that these people spend watching TV is 220 minutes per day. And as computed by the formula that we discussed here, happens to be 35 minutes. Okay, now the question here is to construct a confidence interval. Accepting this confidence level, we now do this. We compute this alpha, which is 1 minus gamma, which now what is this? It's now what's written here, alpha sub t, which is defined to be 1 minus gamma, accounts for these two tails, the right tail and the left tail. So the total probability contained in both tails is denoted by alpha t here. All right, and then df. Okay, let's not make a mistake, a silly mistake. N is 10, but df is n minus 1, which is 9. Okay, and then we consult a table for t distribution. Oh, well, of course, now that personal computers are available and on all sorts of programs. By the way, Excel will provide you with a built-in function for this kind of thing, but conventionally tables are used, and then you get this answer. Okay, this is the t that you get. Okay. Now the half width of the confidence interval then is t multiplied by s root n, and here it's 2.262, 35 root 10, and it's this. Well, if you compare this formula with the formula that we used when we worked with the normal distribution, now z here is replaced by t, and sigma here is replaced by s. But the structure is just the same. So the left boundary is 215 minus 25 is this, and it's this. So the confidence interval is 190 to 215. And again, the interpretation is this. If we conduct the same research many times, then 95% of the time, the true value of the mean will be captured by this kind of interval. Okay? Well, now let's ask ourselves this question. Would it be a big mistake to use the normal distribution instead of the t distribution? Now, t distribution is the exact one. If the sample is large enough, the normal distribution is a good and appropriate approximation for it. But here the sample is not large, okay? It's just 10 points. Would it be a big mistake to use the normal distribution here? All right, let's compare. Now z is 1.96. If we use the normal distribution, which is not warranted here, but if we did this, we would have z equal to 1.96 instead of this one. Okay, and how different are they? Now, if you compare this one with this one, it's about 13% smaller than t. So this value is about 13% smaller than t, which means that by using the inappropriate approximation here, the normal distribution, which is not appropriate here, you'll arrive at a confidence level, a confidence interval that is 13% more narrow than it should be. Okay, this is the price of using the wrong approximation. All right, now let's talk about estimating population proportion. Okay, now what do we mean by population proportion? We mean that x, which is the population variable. Again, the population variable results when we choose at random one member from the population, in which each member possesses a certain individual value of a characteristic. Okay? Now, here we assume that x is of the Bernoulli type. That is, the characteristic is 0, 1. Now, in surveys, in practice, quite often the variables are of this kind. Okay, do you own a car? Okay, do you watch TV series? Do you drink Pepsi Cola or whatever? Okay, there are lots and lots of questions for which there are only two possible answers. And each time we ask this kind of question, we create a random variable of this type. Okay? Now, suppose 25% of all the members in a particular population are regular users of Pepsi Cola. Okay, I'm not trying to advertise for Pepsi Cola, but it's just something that came to mind. Suppose 25% of all the members in the population drink Pepsi Cola. Then by asking this question, do you drink Pepsi Cola, we create a random variable that is of Bernoulli type with probability of success equal to 0.25. So when we perform this, when we conduct this survey, when we ask these questions and receive answers, we just put a 1 in our records for each positive answer and 0 for each negative answer. All right. Now suppose the true proportion is not known and we want to estimate it on a sample. So the proportion is not known. We take a sample of size n, x1, x2, xn. And because x is of Bernoulli type, each of these values is either 0 or 1, binary variable. Okay. Then we can compute what is called the sample proportion, which is x1 plus x2 and sample proportion. Okay. Well, a good way to interpret it is that it's the number of successes on this trial divided by the number of points in the sample. All right, and now if we deal with a large sample, then x bar now when we talk about a Bernoulli type variable, x bar, which is the general term, sample mean, is the same as p bar, which here is called, in this problem, is called sample proportion. Okay, and it's distributed by the normal law And mu here is p, which is not known. And sigma squared is p times q over n. Okay, and so again, please pay attention to this. It only works for a large sample. When we deal with a large sample, by virtue of the central limit theorem, x bar approaches the normal distribution law, even if the underlying random variable is nothing like normal, and a Bernoulli type variable is absolutely not like a normal one. Okay, and then we estimate. And we estimate this. Okay, estimate. And all right, and this is okay. So again, to sum up, we deal with the Bernoulli type variable, which results when we ask a question that admits only two answers, yes or no. We take a sample of size n. These are the sample data, a sequence of values, each of which is either 0 or 1. P bar, which is the same as x bar, the sample mean, which here is also called sample proportion, can be written as the sum of x's divided by n. X bar, due to the central limit theorem, follows, at least approximately, the normal distribution with mu and sigma, where mu and sigma is written in this way. But the true value of p, is not known. It is to be estimated. Now, how do we go about this? We accept p bar, the sample mean, as an estimate for the unknown value of p, and we accept this complex p bar times 1 minus p bar over n as an estimate for sigma x bar. By the way, what I didn't mention, there is a name for this. It's called standard error. Standard error of the proportion. Okay. When we talked about estimating mu, we dealt with a standard error. Sigma x bar is the standard error of the mean, and this one is the standard error of the proportion. All right, let's give it an example. Survey n equals 350. So we interview 350 people and ask them about their nutritional habits, about what they eat regularly. And of those 350 respondents, 72 reported that they eat cereals regularly. Cereals. Okay, such as porridge, a healthy kind of food. So of these respondents, 72 admitted that they eat cereals. Now let's assume this value for confidence interval, and what's the confidence for confidence level, and what's the confidence interval for the population proportion of those who eat cereals regularly, basing on these data. All right, p bar sample mean is 72 over 350, and it's 0.206. And now, how did I write it there? Let's write it this way. This more general notation. Let's use it here. And it's 1 minus P bar, 1 minus P bar n, and it's 1 minus, okay, and 350, and it's going to be 0.022. Okay, and let me continue here. The boundaries of the confidence interval 1.96022 is 1.96 is equal to 0.249. So the confidence interval at this confidence level 0.95 is 163 to this. Okay? Well, there is something to be noticed here. The confidence interval that we obtained here, I would say, is not a very good estimate, does not provide a very good estimate. It's very broad. Look at this. If you report your findings to your boss, you will have to say that you estimate at this confidence level, you estimate the proportion of those who eat cereals to be somewhere between 16% and 25%, okay? Which is a broad estimate. And broad means bad. You would like to have a more narrow estimate here. But, well, let me tell you that it's always this way with estimating proportion, okay? Estimating proportion requires large samples. A way to arrive at a more accurate estimate is to increase the sample size here, okay? Because increasing the sample size will give you a smaller value for sigma x bar. And as a result, you'll have a smaller value of the half width of the interval. Well, if I have a couple of minutes left, I would like to comment on exactly this. Selecting the sample size. Okay. Now, D, and in the problem of estimating the population mean, D is Z times sigma over root n, okay, which can be written as Z times sigma over D squared. Look at this. Whenever you plan field research, it's a necessary step. You need to estimate the sample size that will give you satisfactory answers to your questions. Okay? Now, what means satisfactory? You need to specify the value, the width or half width of the interval that you will be happy with. Can I take up a couple of more minutes? Okay, thank you. So you specify D, which satisfies you as a researcher, okay? But look at this. If you try to make D smaller and smaller, the result will be an increase of n. And because you have a square here, this increase tends to be very rapid when D approaches 0, okay? And the same thing, proportion. Z okay. So for the problem of estimating proportion, we can write this again here. This delta stands for the half width of the interval, and if we rewrite it and look at this, P times 1 minus P attains a maximum value when P is 1/2. Okay, this is the thing. So n is so look at this. You specify gamma, which gives you Z, and you specify delta, and delta is the denominator here. If you try to make delta smaller, the result is an increase in n, a very rapid increase. Just one final thing. Just an example. Suppose you specify this common value for gamma, and you want to arrive at an estimate for the population proportion with the half width of the interval of this, which in common language would mean that you want to estimate the population proportion to within 2%, plus or minus 2%. Do you understand this? So you'd like to estimate the proportion of those who eat cereals to within this margin of error. In popular literature, it's always called the margin of error. So if you want this margin of error, what kind of sample do you need? It's 1.96 squared, 0.25, okay, like this. And this number is surprisingly large. So when surveys for population proportion are conducted, the samples are typically very large. It's very often the case in political polls, okay? The proportion of those who are going to vote for this or that candidate, okay? To arrive at accurate estimates, you have to interview thousands of people. This is typical. Okay, thank you for your patience. See you next time.